How big is it?
We don't know exactly, but it's roughly the size of Manhattan Island. We don't have a close-up photograph of it. And of course, that would have nailed the nature of the object if we had it. If you calculate the path of this object, it will just, as a result of the sun's gravity, get deflected a little bit by about 16 degrees, not much.
Scientists just remeasured 3I Atlas, and the results are alarming. The new data came out, and it's showing something that shouldn't be possible, and honestly, the more we learn about this object, the less sense it makes. Because when they measured it again, they got completely different numbers, and those numbers create a problem that breaks the basic physics of how comets are supposed to work. And on top of that, they just detected something coming from 3I Atlas that they've never seen before on any interstellar object. So let's start with what they found when they remeasured this thing, and why scientists are calling these results alarming. The new measurement. So here's what happened. Harvard astrophysicist Avi Loeb just published new data on 3I Atlas. And the size estimate has changed dramatically, and I mean dramatically because we're not talking about a small adjustment here. We're talking about the object being half the size that scientists thought it was just a few months ago. The new estimate puts the nucleus of 3I Atlas at around 1 kilometer in diameter, and for context, the previous estimates had been sitting at somewhere between 5 and 6 kilometers across. So we're looking at an object that's about 5 times smaller in width than what the scientific consensus said it was. And if you do the math on volume, that means 3I Atlas has something like 125 times less mass than we thought, which is a pretty significant difference. Now, you might be wondering how we got here, and why the size estimate keeps changing, because this isn't the first time the numbers have moved around. When 3I Atlas was first discovered back in July, the initial calculations suggested the nucleus could be as large as 20 kilometers across, and that was based on how bright the object appeared, and some assumptions about what it was made of and how reflective its surface would be. But then, as we got better observations and more data, those estimates started coming down, and by August we were looking at maybe 11 kilometers, and then by September that dropped to around 5 or 6 kilometers, and now we're sitting at 1 kilometer. And this isn't just Avi Loeb making stuff up or pulling numbers out of thin air. The new estimate comes from combining radio observations that were made on July 2, 2025 by the Allen Telescope Array, with data on the comet's non-gravitational acceleration from NASA's JPL Horizons system. And when you run those numbers through the physics of how mass loss creates acceleration on a comet, you end up with a nucleus size of about 1 kilometer. And according to Loeb, this actually confirms the prediction he made back in his first paper about 3I Atlas that was published in early July. So the method here is pretty solid, but here's where it gets interesting, and by interesting I mean alarming, because Loeb himself lists 4 major uncertainties that could throw this whole calculation off. One is that the non-gravitational acceleration data from NASA has been revised multiple times since November, and the way you normalize that data depends on a bunch of assumptions about the telescope images and the models you're using. 2 is that the momentum being transferred to the nucleus might not be coming from gas particles at their normal thermal speed, but instead from fragments of ice that are getting ejected, and those fragments could be moving at completely different velocities. 3 is that we don't actually have any spectroscopic measurements of how fast the jets and material are moving when they leave the surface of 3I Atlas, so we're kind of guessing on that front. And 4, the anti-tail that points toward the sun could be affecting the direction and magnitude of the acceleration in ways that we haven't fully accounted for. So you've got this new measurement that says 1 kilometer, but you've also got all these caveats and uncertainties that could push it back up to something bigger, or maybe even make it smaller. And the reason this matters, and the reason this is alarming, is because of what that size means for the physics of what we're observing. And that smaller size creates a massive problem. Why this is alarming? Because here's the thing about comets and how bright they appear in the sky. The brightness of a comet is driven by how much gas and dust it's releasing into space, and that gas and dust forms the coma, which is that big fuzzy cloud around the nucleus. And the more material you're pumping out, the brighter the comet looks and the bigger the coma gets. And all of that is directly tied to how much surface area you have on the nucleus that can sublimate and release material. And 3I Atlas has been incredibly bright. Back in mid-November, when it first emerged from behind the Sun, it was sitting at around magnitude 10, which made it visible with large binoculars under dark skies. And even now, as it's fading away, it's still at magnitude 13, which means it's still releasing a significant amount of material and creating a substantial coma. And we've measured that coma, and it extends out about 300,000 kilometers from the nucleus, which is almost the distance from the Earth to the Moon. So you've got this massive cloud of gas and dust, and you've got brightness levels that require huge amounts of outgassing. And when you run the calculations on how much material needs to be coming off the surface to create that kind of activity, you end up with numbers that don't work for a 1-kilometer object. Let me put it this way. When scientists were estimating the size at 5 or 6 kilometers, that made sense with the brightness, because you had enough surface area on the nucleus to sublimate enough CO2 and water and other volatiles to explain what we were seeing. But if you shrink that nucleus down to 1 kilometer, you're cutting the surface area by a factor of 25 or more, and suddenly you don't have enough real estate to produce the amount of gas that's required to make 3I Atlas as bright as it actually is. And we know that 3I Atlas is releasing massive amounts of gas because we've observed it directly. The James Webb Space Telescope and other instruments have measured the CO2 production rate, and it's been described as equivalent to a fire hose running at full blast, and we've seen water vapor suddenly appear in late September at levels that were much higher than expected, and we've detected this enormous X-ray glow extending 300,000 kilometers out from the nucleus, which only happens when you've got huge amounts of gas interacting with the solar wind. So you've got all this evidence of violent, massive outgassing, and you've got a nucleus that, according to the new measurements, is too small to produce that much outgassing. And that's a physics problem, because the math doesn't add up. And that's what makes these results alarming. Now, there are a few ways you could try to explain this. One option is that maybe 3I Atlas is way more active than a normal comet, meaning that a much higher percentage of its surface is actually sublimating and releasing gas instead of just being dead, inert rock and ice. That's possible, but it would make 3I Atlas extremely unusual because most comets only have a small fraction of their surface actively outgassing at any given time. Another option is that maybe the surface of 3I Atlas is made of material that sublimates way more efficiently than what we see in solar system comets. And given that this object is between 7 and 14 billion years old and comes from a completely different stellar environment, that's not out of the question, but it's still pretty speculative, and it would require the composition to be wildly different from anything we've encountered before. Or maybe the 1-kilometer estimate is just wrong, and the nucleus is actually bigger, and we'll find that out when we get more observations and better data, and Loeb's 4 uncertainties start to get resolved. But right now, based on the best data we have, you've got a 1-kilometer object doing things that a 1-kilometer object shouldn't be able to do. And that's alarming because it means either our understanding of comets is incomplete or 3I Atlas is something genuinely strange. But the size isn't the only alarming thing they just discovered. The radio signal detection, because on July 2nd, 2025, the Allen Telescope Array in California pointed its radio dishes at 3I Atlas for 7.25 hours and detected something that's never been seen before on an interstellar comet, and that's radio emissions. Now let me be clear about what this means, because when most people hear radio signals coming from space, they immediately think aliens and transmissions and little green men. And that's not what we're talking about here, but it's still significant because 3I Atlas is now the first interstellar comet ever observed in radio wavelengths, and that's a pretty big deal. So here's what the Allen Telescope Array picked up. They were observing in the frequency range between 1 and 9 gigahertz, which covers a pretty wide band of radio spectrum. And over the course of that 7.25-hour observation window, they detected nearly 74 million narrowband hits. Now, most of those hits are just noise or interference from satellites or ground-based radio sources, so the team had to go through and filter everything out. And after accounting for radio frequency interference, they were left with about 2 million hits that seemed potentially interesting. Then they took those 2 million hits and started checking whether they actually coincided with the position of 3I Atlas in the sky, because you don't want to just assume that every radio signal in the general area is coming from the comet. And after filtering by sky localization, the vast majority of those signals didn't line up with where 3I Atlas was supposed to be, so they got ruled out. What they were left with was 211 hits that were visually inspected in the time-frequency domain, and those 211 signals did seem to originate from the direction of the comet. And when they analyzed the power output of these radio emissions, they calculated that 3I Atlas was radiating somewhere between 10 and 110 watts of isotropic radio power within the observed frequency range. Now, that might not sound like a lot, but for a natural object that's not a star or a pulsar or some other exotic source, it's actually pretty significant. And the fact that we're detecting radio emissions at all from an interstellar comet is completely unprecedented. So what's causing these radio signals? Well, the most likely explanation is that it's the same basic process that creates X-rays around comets. When 3I Atlas releases gas from its nucleus, that gas expands out into the coma, and eventually it starts interacting with the solar wind, which is just a stream of charged particles flowing out from the sun. And when those charged particles collide with the neutral molecules in the coma, they create X-rays, and they can also create radio emissions through a process called synchrotron radiation or through other plasma interactions. And that makes sense, and it's a natural phenomenon. And there's no reason to think this is anything artificial or alien, but here's what makes it alarming. We've observed plenty of comets in radio wavelengths before, including comets from our own solar system, and we've never seen this kind of radio emission profile from an interstellar visitor. And the fact that 3I Atlas is producing detectable radio signals while also being way smaller than expected, and also producing way more gas than it should be able to produce, all adds up to an object that's behaving in ways we don't fully understand. And the team that made this discovery knows that we need more data, which is why they're planning to re-observe 3I Atlas in December 2025 to see if the radio emissions have changed or evolved as the comet moves farther from the sun and starts cooling down. And if those December observations show something different or unexpected that's going to add another layer to this mystery. And remember how I said there was something else about 3I Atlas that we still can't explain? Well, it's still doing that. The anti-tail, and what happens next. Because the anti-tail that first showed up in Hubble Space Telescope images back on July 21st, when 3I Atlas was still 2.98. Astronomical units from Earth is still there, and it's still pointing toward the sun instead of away from it. And nobody has a satisfying explanation for why that's happening. Normal comet tails point away from the sun, because that's how solar wind and radiation pressure work. And we've observed this on every comet we've ever studied, and it's basic physics that the pressure from sunlight and the flow of charged particles push the gas and dust in the coma away from the star, and that creates the tail. But 3I Atlas has this prominent jet of material that extends for about 1 million kilometers in the direction of the sun, and it showed up in the first Hubble image, and it was still there in the second Hubble image taken on November the 30th, and it's still there in the most recent observations from mid-December. And Avi Loeb has written 3 separate scientific papers trying to explain the physics of this anti-tail, and his explanations are pretty technical, but the basic ideas are that maybe it's caused by tiny fragments of ice being shed from the sun-facing side that evaporate before they get pushed back by radiation. Or maybe it's a swarm of objects lagging behind the comet because of the way non-gravitational acceleration affects different size particles. But even with 3 papers and months of analysis, there's still uncertainty about what's actually creating this structure and why it's so persistent and so tightly collimated. And here's what makes this particularly frustrating. NASA held a press conference about 3I Atlas back on November the 19th, and you can go watch the recording online, and they talked about the trajectory and the composition and the observations from Hubble, and they discussed the CO2-rich coma and answered questions from reporters, but at no point during that entire press conference did anyone bring up the anti-tail or acknowledge that there's something unusual happening with the tail structure that we don't fully understand. And maybe that's because they didn't want to fuel alien speculation, or maybe they thought it was a minor detail, but either way, it feels like a significant omission when you're giving the public an update on an object that's breaking the normal rules of comet behavior. So you've got the size problem, and you've got the radio signals, and you've got the anti-tail, and all of this is happening while 3I Atlas is fading fast and getting harder to observe every single day, because right now it's sitting at magnitude 13 and dropping. And by the end of December it'll be magnitude 14 or dimmer, and by January it'll be magnitude 15, which means only professional astronomers with big telescopes will be able to track it. And this creates urgency because we've got a very narrow window to learn as much as we can about this object before it becomes too faint to study effectively. And the December 2025 re-observation that Loeb and the radio astronomy team are planning is critical, because that's one of the last good chances we'll have to see if anything changes, or if we can resolve some of these uncertainties about the size and the activity and the radio emissions. And then after December, the next major milestone is March 16, 2026, when 3I Atlas will fly past Jupiter at a distance of about 53.6 million kilometers. And we've got the Juno spacecraft in orbit around Jupiter right now. And there's a possibility that Juno could observe the comet during that flyby and get some final images and data before 3I Atlas heads out toward the orbit of Neptune and eventually back into interstellar space. And after that, Jupiter flyby in March, it's basically over because 3I Atlas will be beyond Neptune by late 2026, and by 2027, it'll be back in the void between stars, traveling at 148,600 miles per hour away from us, and it will never come back, and we will never see it again. So this is it. And this is why these new measurements are so alarming, because we're running out of time to figure out what 3I Atlas actually is, and whether it's just a really weird comet, or whether it's something that challenges our understanding of how these objects form and behave. We've got an object that's way smaller than we thought, but way more active than it should be, and it's producing radio emissions that we've never seen before from an interstellar visitor. And it's got a tail pointing in the wrong direction that nobody can explain, and we've only got a few more months to study it before it disappears forever. And there's still this ongoing debate about whether we should try to send a spacecraft to intercept 3I Atlas before it gets too far away, and that decision needs to be made in the next few weeks, because the launch window is closing and every day that passes makes the mission harder and more expensive and less likely to succeed. The European Space Agency looked at it briefly and decided the timeline was too tight, and NASA has the capability, but they need congressional approval and funding, and private companies like SpaceX have the rockets, but somebody needs to pay for it, and meanwhile 3I Atlas keeps getting farther and farther away. So we're left with all these questions and all these alarming results and a ticking clock, and the very real possibility that we're going to let the weirdest interstellar object we've ever encountered slip through our fingers without ever really understanding what it was or where it came from or why it behaves the way it does. And that's the situation we're in right now with 3I Atlas. It was measured again, and the results show something that shouldn't be possible, and we've detected radio signals for the first time, and the anti-tail is still defying explanation, and we've got weeks or maybe months left to figure this out before the opportunity is gone forever. So here's my question for you. What do you think is more likely, a 1-kilometer comet that somehow breaks the rules of physics and produces way more gas than it should be able to, or a 5-kilometer comet where all of our instruments and measurements are somehow getting it wrong? Let me know what you think in the comments, because honestly at this point both options seem pretty wild. And if you want to stay updated on what happens with the December re-observation and the Jupiter flyby in March, make sure to subscribe and hit the notification bell, because this story is far from over, and we'll be covering every new development as it happens. Thanks for watching.